Okay, so hello everyone. Week four of welcome to the week four of problem solving session for hi Akansha for the discrete maths course. Okay, so this week what we will do is we will take a look at some of the solutions for um, your assignment 1 and 2. So not all of them, but maybe the ones that you want me to specifically discuss, and then we will take a look at some problems based on the topic for this week, which was relations. Okay, so so that is how we will proceed. So I'll start with the questions for assignment 1. So last time I think um, yeah, last time I think there were doubts about question 1, 4, 5 and 10. So I think 1 and 4 we briefly discussed. So what I'll do is I'll do 5 and 10, but additionally if there are any other questions that you want me to take up, then let me know right now. Okay. Okay. So is question 4 fine with everyone? We briefly discussed it last time, or do you want me to start with that? So then please let me know. Okay, good. So we will take a look at question 5. Um, okay. Okay, so you have a couple of counting problems that are listed. So I'll just write them down. So one is that you want to count. Sorry. Mm, okay. One is the number of ways. Okay. So there's a table around which okay, assume this is a table. So there's a table around which n people are seated, and you want to count the number of ways in which they can shake their hands. So let's say this is one person sitting here, this is another person sitting here, and so on. So when I draw this line, what this means is this person A and this person B and this person B, they shake their hand. And let's say I draw a line here, then what that means is this person C and D, they shake their hands. But then I cannot draw this because these two would be crossing. So this is something that is not allowed. So that is your first question. And the second question is the number of ways in which you can write the balanced parenthesis. So what do we mean by that? If you have um, yeah, I mean at any point the number of opening brackets that you see is at least as many as the number of closing brackets that you see. So these are your balanced parentheses. And C is that you have some x many black balls, then you have some red balls, and you want to pick 4 red balls out of it. And D is that okay, and D is that you have a polygon. So let's say you have a hexagon, and so this is a 6gon or a hexagon, and you want to do some triangulations. That is, you want to draw edges like this, which uh, partitions your polygon into triangle. So this is a triangle, and so on. So the number of ways in which you can do this is what the question asks. So the one context in which we saw Catalan number is the number of um, monotone walks without crossing the boundary. So this is in fact what the fourth question is talks about, and we saw that this number is 2n choose n minus 2n choose n plus 1, and you simplify this turns out to be this, and this is what your nth Catalan number looks like. And what this question asks you is which of these A, B, C, D. So you have you have 4 counting problems, and the question is which of these answers would turn out to be equal to the Catalan number. So let's see how do we do that. So okay, so before I get into the idea, does anybody of you have any thoughts or any ideas about how to show this? Okay, so okay, that is fine. So we'll take a look at this. So at least you agree that this problem 1, which is the number of ways in which you can count the number of paths which do not cross the boundary, so that is equal to this number. So what we will do is, for each of these problems we will try to obtain a bijection. So what do I mean by bijection? So you have a function f here. So this is a proof technique which is called proof by bijection or counting by bijection. And what you do is, you have a set here, a set A here which has some elements, and you want to estimate the size of this set. Okay, so what you do is, you convert it into another problem, or say another set, such that every element here has a unique image here. So there is a function that gives you a unique image for each of the elements here. So so it's sufficient to count the size of B, which is easy to count typically, and then you know, and therefore this gives you the size of A. So that is the idea. So if you want to estimate the size of a set, what you do is, you convert that problem by showing a bijection into some other set B, which is typically easy to count, and once you know how to count B, you have a count for A. So in this case, what we will do is, say let's say I am picking up this problem B, which is the number of balanced parentheses. So I want to show that the number of balanced parentheses is equal to this Catalan number. So what one way to do that is to design a whole an entire proof for showing this. Another way is that I already know that the count for this problem is equal to Cn. So what I'll do is, I'll simply give a bijection from this set to this set. Okay, so is the idea clear? Yeah, please let me know if there are any questions. Okay. So this is your balanced parenthesis problem. Okay. So anybody has any idea how to define this function f, which goes from, so in this case on side A uh, you have all possible balanced parentheses, and on the right side you have the set of all non-crossing non-diagonal crossing paths. So anybody has any idea how to associate this? Okay, so yeah, uh, exactly. So Akansha says that let's say you have a parenthesis, and let's say you want to take a walk from 00 to 22, because in this case the uh, 2n is 4 for us. So yeah, so what does that correspond to? So sorry. Okay, so what does that correspond to? So let's say you see a left bracket, then you move to the right. If you see a left bracket again, then you move to the right. When you see a closing bracket, you move upward, and when you see a closing bracket again, you move upward. So this gives you one path which is not crossing the diagonal. So let's say suppose just for the sake of example, let's say this is the bracketing I had. How do you convert it to a path? Can somebody tell the sequence of left and right moves, just so that it is clear to everyone what the mapping is? Okay, yes, good. So you see the left bracket, you move to right. You see an opening bracket, you move to left. You move upward, you see a left bracket, you go to the right. When you see a closing bracket, you go up. So this path, again, as you can see, does not cross the diagonal. So this also is intuitive, because notice that when do you say that a parenthesis is not balanced? That happens precisely when the number of left brackets that you are seeing uh, exceeds is less than the number of right brackets that you see. So for example, if I had something like this is not balanced. It has equal number of left and equal number of right brackets, but this is not balanced. So this also happens in the case of walks. In the case of walks, what happens is, if you take more upward moves than the number of right moves, then you would have crossed the diagonal. So if you do something like up, right and up, then you would have already crossed the diagonal at this point. So it's because of the nature of the properties that is common to both, that you can see such a bijection. So I'll just write it formally here. So the bijection function phi, which maps A to B, this is the balanced parenthesis, and this is the non-crossing paths. I mean the set of, and this is the set of non-crossing paths. Okay, so this is what you have, and like Akansha pointed out, what does the function do? It takes a bracketing, so let's say B, and what it does is, if it converts it into a string of rights and so this would be a string of rights and lefts of length 2n, such that number of rights is n. So what you do is, if you see a left bracket, then right, or let's say append with, or let's say then move to the right, and if you see a closing bracket, then move upward. So this is the bijection that you have, and it is not, so what we did is we just defined what the function is, but it is not enough to just define the function. What you need to do is you need to show that you need to prove formally that phi is a bijection. So what do you mean by that? If um, yeah, if you have two uh, if you have two different balanced parentheses, say b1 and b1 and b2, then it has to be that phi of b1 is different from phi of b2. So this is something that you can try to prove. So in other words, we are saying that the function is 1 1 as well as on 2. So this is something that you can take as an exercise, but what I wanted to show uh, is that if you want to show that the count of some object is same as Catalan number, either you could explicitly go on and do that, or what you could do is you can appeal to the idea of bijection, which is that on the left side you have the set of objects you want to count, on the right side you have something which you already know, whose count you already know, and then you just show the bijection. So this is what we had in this case. And okay, I think this yeah yeah so this problem of people sitting across a table and shaking their hands is very similar to this problem where you have a polygon and you are drawing triangulations. So does anybody see similarity between the problem A and problem D?
Yes, ma'am.
Okay.
The vertices of the polygon can be seen as peoples, and the line joining them can be seen as their shaking hands.
Yes, exactly. So you can think of this vertices as people, and you draw an edge when they shake hands. So when we say we want a triangulation, we are implicitly saying that you do not want edges that cross each other. We don't want two diagonals crossing each other. So it is similar in that spirit. So so what you can do is, as an exercise, try to show a bijection between A and B. So from A you can try to go to B, or from D you can try to go to A. So both are essentially the same things. What we did so far is we did B to the monotone walk, and about let's say you want to show a bijection from this triangulation problem to um, to any of the problems whose count is Catalan number, then anybody has any idea how to proceed?
Ma'am,
Mm-hmm.
we can take any polygon like pentagon or hexagon, and we can apply the condition given in question, and then we can match the value, uh, and then we can put the value of triangles uh, we get in chosen polygon and put it in this Catalan number,
uh,
and then if we get the same answer, then we can say that it is a Catalan number.
Okay, so let me just repeat what you said. So I just want to be clear that I understood your idea. So what you're saying is that you start with n equals 3, n equals 4, which is square, pentagon, hexagon, and so on, and you try to find the number of triangulations that are possible, and you try to match it with the Catalan number, and if that happens, then you know that the count matches. Is that what you are suggesting? Okay, so so one problem with that is, let's say you try this for n equals 3, and your answer matches with the third Catalan number. You try for n equals 4, your answer matches with um, the fourth Catalan number, and let's say you go up to 100 and your answer matches with the 100 Catalan number, and you're lucky until this point. But what if say your 101th, if you look at a 101 polygon, uh, I mean, a polygon with these many edges, sides, then what if your answer say is C101 plus 10? Because when you say n, this is an infinite series, so no matter what n you give me, the answer is always going to match with this. So one problem with like explicitly counting for values, for some values of n, is you don't know if at some point in future it is going to violate the Catalan number, and you can't exhaustively calculate all of them because they are infinite. Is that making sense? Okay, good. So yeah, anybody else, any questions about whatever we discussed so far? Okay, so okay, so what I'll just leave you with this thought that if you want to show that um, that the answer is Catalan number, of course one thing you can do is, like O just suggested, you can try to explicitly write the values for small values of n. But if you see at some point that it does not match with Cn, then you can say for sure that the number is not a Catalan number. But the problem is, if the answer is indeed a Catalan number, you can't infinitely keep on doing this process. So you need something like a proof technique to be able to say that this number is precisely the Catalan number. And one way to do that is bijections. So we saw bijection from from B, and I'll leave it as an exercise for you to try this out. Try bijections from A and D. C you would not be able to do, because obviously the answer is not a Catalan number. So I hope that that part was clear. So it's just a counting problem where you have 16 black balls, 6 red balls, and 13 blue balls, and you're just picking a red ball from it. So yeah, so you can only yeah yeah, I mean, that is obviously not a Catalan number problem. But yeah, if there are any questions, or if you would want me to say more words, then let me know. Okay, and okay, so I hope question 10 was fine. I mean, I agree that none of the options are correct, and I hope they'll look into the issue. But I hope this part was, I mean, you know your answer well, or do you want me to discuss this one? Okay. Yeah, are there any other doubts about assignment 2, other than the fact that some answers are not matching? I mean, conceptually, are there any questions on the week 2 assignment? Okay, so then shall we start with the new set of questions for this week? Okay, good. So, okay. Um, okay, so what I'll do is I'll quickly recall what relations are and the representations of them, and I'll solve this A part for you, and then you can try out the B part. So, what are relations? Relations is simply okay. Say you have sets A and B, and you define R to be a subset of A cross B, and this cross is a Cartesian product. So, for example, say A is 1 2 3, and say B is 2 4, then A cross, how many elements does A cross B have?
Six.
Ma'am,
Mm-hmm.
6 elements.
Yes, good. So this is what I'll just write few elements, and I think this is, yeah, okay. So this has 6 elements, and a relation defined on A cross B would be a subset of this. So for example, 1 2 2 2, this is a valid relation because it's a subset of this set. But something like 1 2 um, 1 2, let's say 5 2, something like this is not a valid relation because this element is not in the cross product. So that is simply what relations are. And now the question is, of course, so one point is that a function is also a special case of relation where I mean for okay, I'll not get into it, but I hope it's pretty clear that a function is also a relation. So now the question is, if A and B are like very large sets, then you want a better representation for the relation. You want a visual representation for the relation. So there are two popular representations that are generally used. One is the graphical and the other is the matrix form. So let's look at this particular example. So okay, so let's look at this example A. So what I'll do is, I have this set of 1 2 3 4. So I'll draw it this way. So the elements are the nodes for me. So whenever I see a graph, I have vertices and edges associated with them. Okay, so the vertices for me are the elements of this set. And when do I draw an edge? I draw an edge if two nodes are related. So 2 is related to 2. So I'll draw a self edge like this. 2 is related to 3. So I'll draw an edge like this. Note that this is directed because 2 3 being in the set is not the same as 3 comma 2 being in the set. In this case it so happens, but in general it need not be. So the other edge would be 2 to 4, then 3 to 2, 3 to 3, and 3 to 4. So this is the graphical representation. And the other representation is what is called matrix representation, and this is very popularly used. So what do you do? It's you write the elements in the set in the rows, and you write the elements in the columns, and then uh, each each cell here is going to take a value of 1 or 0. So this is going to be a 0 1 matrix. And how do you fill the value? You write a 0 here if 1 and 1 are not related. So let's do this with example. So in this case 2 and 2 are related, so I'll look at the second row, the second column, and write a 2 here because they are related, sorry, and write a 1 here because they are related. Whereas 1 comma 1 is not in the relation, so that would be a 0. Similarly 1 comma 2 is not in the relation, so that would be a 0, and so on. So you can keep on doing this. Then you have 2 4, 3 2, 3 3, 3 4, and the rest of them would be zeros. So that is how you write the matrix representation. So the number of ones in this 0 1 matrix would be exactly equal to the number of elements that are there in the set. Okay, so are there any questions about any of the, I mean, the definitions of relation or the two representations that we saw? If there are questions, then let me know right now, or you could try this part B. I'll wait for a couple of minutes and then you can let me know your answers.
Then in graphical representation, can we have a disconnected graph like this?
Yes, yes, that is perfectly possible. So the graph need not be connected. So a relation does not impose that constraint. Okay, so anybody, would you like to tell your answers? So the vertices are clear. It is the same as yes, Ojas.
Ma'am, we can draw loops to all numbers.
Okay, that is right. So one is related to one, two is, and so on. So you only have loops and you don't have edges from one vertex to the other. And in the matrix form,
We can put ones in the places on diagonals and zeros in rest of the places.
yes. So along the diagonal you have ones because one is related to one, two is related to two, and so on for three and four. But you do not have any other, um, yeah, I mean any other pairs that are related. So everything else would be zero. Okay, good. So yeah, so that was just a quick definition. So the second question is also similar, but maybe just take a couple of minutes. So here you are given a relation, and you're asked which of the following four is the correct graphical representation. So I'll wait for a few minutes. You can let me know in the chat, or you can unmute and tell me.
I think C is the.
Okay. Um, yeah, I think that is correct. So what happens in for example b is you do not have a self loop. Here you have a to a, then you have a to b, then you have b to c, you have c to b, then c to d, d to a, and d to b. Yeah, good. So c is the correct answer, and I think in the rest of them you would end up finding something which is malicious and does not match with the relation r. Okay, so good. um, okay, so I'll quickly recap uh, some definitions that are useful for this question. Okay, so okay, so I'll call this some properties of properties of relations. So um, okay, so um, okay, maybe I'll just write them down and then I'll talk about this. So there are four properties. One is what is called reflexive, one is what is symmetry, third is antisymmetry, and fourth is transitive. So okay, so what do we mean by reflexive is that if let's say Maybe I'll take an example. So I'll take probably the same example that was done in the class. So let's say you have a group of people. So there are some n many people in here, and you say that A is related to B if say they are friends, and assume that if A is friend of B, then B is also friend of A. So okay, okay. So you say that a relation is reflexive if A is related to A for all A. So if every person is a friend of themselves, then you say if that happens, then the property is reflexive. And if A is related to B, and that implies that B is related to A for every pair of AB, then you say that it is symmetric. So for example, if let's say A plus, I'll maybe take a better example. So R is a relation of all AB such that A plus B is even. Okay, so yeah, so in this case, if a is related to B, then this implies that B is related to A, because if A plus B is even, then B plus A is also even. So in this case, if a relation satisfies this property, then you say it is symmetric. Antisymmetry would be the opposite of that. So A is related to B and B is related to A implies A equal to B. So okay, maybe I'll take this up with example. So even if it is not, I'm just trying to recall. If you have seen these definitions in the lecture, then I'm just trying to recall it with the definition. But I'll talk about this more when we come to the examples. And transitivity is something you must be knowing, or you must have seen already. So if A is related to B and B is related to C, then by transitivity this says that A should be related to C. So it's something like if A is a friend of B and A and B are friends and B and C are friends, then it better be that A and C are friends. So if this property is satisfied, then you say it's transitivity. So even if this does not make
And
sense,
in transitivity, the order matters. That is, if A is related to B and B is related to C.
yes, the order matters. So if it is that C is related to B, then you can't. I mean, you need not put this restriction. Yeah. So it has to be strictly in this order. Okay. So okay. So I'll let you think about this question now. So you have this set 1 2 3 4, and the relation is defined like this. So this is a matrix representation. You can think of this as 1 2 3 4, and the columns marked as 1 2 3 4, and if you look at the corresponding cells, it will tell you whether the elements are related or not. So the question is whether they are reflexive or symmetric. So we're not talking about antisymmetry or transitivity at this point. We're simply asking about reflexivity and symmetry. So reflexivity says that for all A is related to itself. Symmetry says that for all AB, A related to B implies B is related to A. So um, okay, maybe uh, okay, I see a couple of answers. Yeah, I'll just wait for a minute for others to think, and then we will discuss this. Okay, so yeah, I just have one request to all of you. Those of you who are attending, if I mean, if you're trying to solve the question, then please. I mean, please let me know what you think in the chat, your answers or your partial ideas or anything, because even if it's very easy for you or even if it's hard for you, if you let me know either by chat or unmuting, then it helps me gauge where you are. So it would help me tell you address at that level. So I encourage you to participate. That would help me. Yeah. So okay. So I see a couple of answers. So which is correct. So the answer is that it's both reflexive as well as symmetric. So it's reflexive because um, for for 1 you see that 1 is related to 1, 2 is related to 2, 3 is related to 3, and 4 is related to 4. So across this diagonal, if you see all ones, then that means that the relation is reflexive. And about symmetry, um, the nice thing about this matrix representation is that if you look at let's say I'll clear this up. Okay, so if you look at 1 comma 2, okay, so if you look at this entry 1 comma 2 and 2 comma 1, what happens is that they are located um, as transposes of each other. So 1 comma 3 and 3 comma 1, they are in the transpose position, these two, and so on. So um, so what that means is, if you see a value here, you see the same value here. This If you see a value here, it's the same as here. And so basically, instead of looking at row comma column, you look at column comma row, and this is what you get. So this matches with this value matches with this, and this value matches with this. So R is same as its transpose minus the diagonal. So if you're familiar with matrix and the transpose operation, this is what it means in terms of matrix. And in this case, it so happens that the values match. So one way is you can look at pair by pair and try comparing whether if a comma b is there, then is b comma a also one. That is also there, but since it's a matrix representation, it's easy to see this way. So in this case, it so happens that the values match with their transposes, and therefore this is symmetric. So the answer is reflexive and symmetric, which is what most of you answered. But yeah, I just have one additional question to pose. So let's say instead of the matrix form, let's say um, you were given a graphical representation. So let's say you have a relation R which is symmetric. Um, then let's say G is a graphical representation of this. So what can you comment about the edges of G? Is there any peculiar property that you can see?
Yes, ma'am. There is a property. The line joining the two elements or 2 points is of two arrows. Means the line is pointing towards the points you are joining.
Exactly, good. So
It's bidirectional. The edge is bidirectional.
exactly. So yeah, so basically A is related to B, so you have an edge like this, and because of symmetry you are forced to have an edge from B to A. So if you have edges, they would always look like this. And let's say it was um, let's say it was reflexive,
It's loop.
then it will be self loop everywhere. So for example, the first example that you saw, this one where you only had self loop, this was reflexive. This relation is reflexive. What can you say about symmetry?
I think there isn't symmetry in this case.
Yes, that is correct. So this is also symmetric because if you look at the matrix representation, um, if you take a transpose of this matrix, it will be exactly both the matrices would exactly match. So this is, yeah. So that was one quick example. Um, yeah. So next, Yeah. So next we'll talk about this reflexive, symmetric, antisymmetric, as well as transitive property. So what I'll do is, just so that the definitions are very clear, I'll start with the first example. I'll solve it. Then I'll let you figure out BCD. So R is a relation. So you have a set of people, and you say that A is related to B if A is taller than B. So let's ask if is this reflexive. So is A,
No.
yes, good. So A is not taller than himself or herself. So clearly this is not reflexive. What about symmetry?
It is not symmetric.
Yes,
Not
because,
sure.
yes, good. So because if A is taller than B, then B cannot be taller than A. So I'll write this, whenever I write this, I mean it is not related. So I'm R followed by this slant. What about antisymmetry? Yes. So yeah, so I have one answer which says yes. So indeed, this is an antisymmetric relation. What we mean by that is, if A is related to B, mm, then B cannot be related to A unless A is equal to B. So that's the only exceptional case that you have. So what we're saying is, if A is taller than B, then it can't be that B is taller than A, which is true in this case. Therefore, this is an antisymmetric relation. What about transitivity?
It is a transitivity.
Yes, it is transitive because if A is taller than A is taller than B and B is taller than C, then clearly A is also taller than C. So this is a transitive relation. So it is not reflexive, it is not symmetric, it is antisymmetric and transitive. Um, so yeah, if there are any questions about this, then do let me know. Otherwise, please try out B.
Ma'am,
Mm-hmm.
the answer for B, it is a reflexive relation. It is a transitive relation. It is not sorry. It is a symmetric relation. It is not an antisymmetric relation, and it is a transitive relation.
Okay, good. So let's see that. Okay, so let's ask if this is reflexive. So, so clearly A and A are born on the same day because they are the same person. So A is related to A for all A. So this is a reflexive relation. Let's ask symmetry. So if A and A is born on the same day as B, then clearly B is born on the same day as A. So, yeah, so this is indeed a symmetric relation, and if it's symmetric, it can't be anti-symmetric at the same time, because if A is born on the same day as B, then B can't be not born on the same day. So, clearly this is not anti-symmetric. And what about transitivity? Say A is born on 6th of March and say B is born on the same day, and so A and B are related. Let's say B and C are also related, so that means C was also born on 6th of March, and that directly implies that A and C are born on the same day. So this is transitive. Okay, so yeah, So that is your answer for B. And what about C?
Oh, ma'am, it is a symmetric relation. It is not an antisymmetric relation. It is a transitive relation.
What about reflexivity?
And yes, it is a reflexive relation because A and A has same, they are the same
Exactly.
person.
Yes, good. So B and C, they are essentially the same answers. So this is also reflexive, this is symmetric and transitive, but it is not antisymmetric. Good. And what about the last one?
It is reflexive. It is symmetric, not an antisymmetric, and transitive also.
Okay. Anybody else has a different answer for D? Isha, Pratik, Akansha, Ritu, any of you? Okay, so let's take a look at this. Um, say D is that this is a relation of AB if A and B have a common grandparent. Okay, yeah, Akansha, you're right. So this let's see this. Uh, okay, so so like Ojas said, this relation is reflexive because A and A, they have the same grandparent. So this relation is reflexive. That is obvious. What about symmetry? If say A and B, they have some common some common grandparent here, then clearly B and A have the same common grandparent. Does not make a difference what order you take. So it is symmetric, and since it's symmetric, it can't be antisymmetric. So this is not there. And the tricky part is about transitivity. Okay, so let's maybe take this example. Say A and B have a parent. um, let's say A has a parent C and C has a parent D, and D has some other child which is E. And okay, I'll just write this. Okay, so the example that I'm looking at is that A and B, they have a common grandparent which is D. So A is related to B, and B and C, they have a common grandparent which is F. So B is related to C. But if you look at A and C, do they have a common grandparent in this diagram? No, exactly. So A is not related to C. So it is not that if A and B are have a common grandparent and B and C have a common grandparent, then necessarily A and C must have a common grandparent. So this relation is not transitive. If you want to show that some property is not true, you can just give a counter example like we did in this case. So that would be enough to show that a relation is violating some property. Okay, good. So, are there any questions about any of the four questions that we saw? Okay, so yeah, I'll move on to the next question. So, you're given a relation which is defined like this. So, you say that PQ is related to RS if p minus s is equal to q minus r. So this is a set of integers. PQRs is our set of integers, and this is the relation that is defined. So the question is, what can you say about reflexivity, symmetry, properties of this relation?
Man, I don't think this relation can be reflexive.
Okay. Yes, good.
And it is a symmetric relation.
Sorry, could you repeat that?
Um, this relation is a symmetric relation.
Okay, okay, good. Um, okay, so let's see this. So the if you want to understand whether it is reflexive, let's ask if PQ is related to PQ. So if you do that, what you get is P minus Q on one side, and you have Q minus P on the other side. So it's not uh, it's not necessary that P minus Q is same as Q minus P. So for example, you can take 2 3 and 2 3 as your examples. So 2 minus 3 is not the same as 3 minus 2. So this is a clear counter example of why the relation is not reflexive. So therefore this is not reflexive. To understand symmetry, say PQ is related to RS, and what that means is P minus S is same as Q minus R. Okay, now let's understand what is RS related to PQ implied. So if this were true, then what would that mean?
It would be R minus P is equal to S minus Q.
Uh, is it R minus P or is it R
Uh,
minus Q?
no. R minus Q is equal to S minus P.
Exactly. And if you yeah, if you multiply both sides by minus 1, then what you get is Q minus R is same as P minus S, which is what you already know. So if PQ is related to RS, then it implies that RS is related to PQ. So PQ RS in relation implies RS PQ is also related, and therefore this implies that the relation is symmetric. So is this fine with everyone? Otherwise, please let me know. So the answer is A. Sorry. The answer is not reflexive but symmetric. Is this fine with everyone? Okay, good. So I'll move on to the next question. So mm, okay. Okay, so you have a relation which is defined like this. So two elements x and y are related if and only if say x plus y is 0. So the question is the same. You want to find out whether they are reflexive, symmetric, antisymmetric, or transitive. So what properties are true is what the question is. So maybe try out the A part for a couple of minutes and then we will discuss.
Ma'am,
Mm-hmm.
can we say a relation is symmetric if only one of the elements has its repetition? Like
No, no. That is a good question. So a relation is symmetric only if every element satisfies the property. So that's why in
Uh,
order, huh.
and can we say relation is reflexive if one of its element does repetition? Means a comma a is valid, but a1 comma a1 is not valid.
No. So every relation that would every property that we define must hold for every pair of elements. Only then you
O-
say
Okay, ma'am.
okay, good.
Then the answer for part A would be this uh, option A is not reflexive, it is symmetric and it is not antisymmetric.
What about transitivity?
No, it is not transitive.
Okay, good. So let's solve this. Others, if you are trying out, please let me know in the chat, or you can unmute and tell me. So meanwhile, we will try to solve this. Eh? So this is set of all x y such that x plus y is equal to 0. So the first question is this reflexive? So for this to be reflexive, you would have to have that x plus x is equal to 0, and this can only happen if x is 0. But for example, one thing I probably forgot to mention is that the set that we are looking at is the set of real numbers. Okay, so for example, if x is 1, then x plus x, which is 1 plus 1, is not equal to 0. So the reflexivity property is violated here. So this is not reflexive. Let's ask if this is symmetric. So x plus y, let's say x is related to y, that means x plus y is equal to 0, and by uh, commutative property of addition over real numbers, this also means that y plus x is 0, and this implies that y is related to x and therefore symmetric. So the third thing is about antisymmetry, and clearly if a relation is symmetric, it cannot be antisymmetric at the same time. So this is clearly not the case. And let's take a look at transitivity. So let's say x is related to y and y is related to z. What that means is x plus y is 0, y plus z is 0. So what can you say about x plus z? Does anybody see a counter example? Okay. Uh, okay, so I think you think, Pratik, I think you're thinking on the right lines, but I think z is x. So I think what you're thinking is right. So since x plus y is 0, y is same as minus x. And if you put it here, you get minus x plus z is 0. This means z is 0. Z is x. And if you put this here, x plus z would be x plus x, which is 2x. And that's why this need not be this need not be 0. So for example, if x were 1, x plus z um, would have been 2. So this is not equal to 0. So I think what you're thinking was right. Just okay, yeah, no problem. So this is violated, just not transitive. Okay, good. So I'll let you try out the B part. Maybe take a couple of minutes and then we can discuss this.
Ma'am, it would be reflexive, symmetric, not antisymmetric, and transitive.
Yes. Transitive. Okay. Yes. Okay. I think Isha also. Okay. Isha and Pratik. Yes. Let's. Sorry. Okay. 1 second. Okay. Is my screen visible now? Okay. So let's try this one out. Um, so you have this relation which says that uh, x and y are related if xy is at least 0. So let's ask reflexivity. So is x related to x? Is it true that x times x, which is x square, is greater than equal to 0? So this is always true because square of any real number is positive, is at least yes, is because square of any number is at least 0. So reflexivity is true. And let's ask symmetry. So symmetry says that, say x is related to y, then xy is at least 0, that means yx is at least 0, that means y is related to x. So this is symmetric. uh, and yeah, like we've been saying all this time, if a relation is symmetric, it is clearly not antisymmetric. So uh, yeah, so you don't need to check this, but let's try out the transitivity part, which is the interesting part of this. So let's say x is related to y and y is related to z. What that means is xy is at least 1, is at least 0, yz is at least 0. Does that imply that, is it true that xz is at least 0? Okay, good. Okay, good. So Tejas and Nakansha, I think you're right. So why is that? So let's say xy is at least 0. What that means is either x is positive or x is negative. In that case, y has to be positive, because if x were a positive number and y were a negative number, and if you multiply them, you would have ended up getting a negative number. So either both of them should be positive or both of them should be negative. Okay, and now you have from this relation that yz is at least 0. So in the case 1, what can you say about z? Is z positive or is z negative? So if the product is positive and one of the elements is, positive, the other element has to be positive. Otherwise, like we said earlier, the product would end up getting negative. What can you say about this case? Yes, I just you have a question.
Ma'am, I think it is not transitive. Means if x is positive and y is 0, then the product would be 0. And in other case, y is 0 and z is negative, then the product is 0. And we take x as positive and z as negative, so their product is less than 0. So I think that's not valid. So it is not transitive.
Okay, yeah, yeah. I think that is correct. So this analysis that we're doing would work only if you have a strictly only if this were a strictly greater than 0 condition. If the moment you have equality, it changes the scene. So I'll just complete the analysis, then I'll come back to your point. So good for pointing that out. So yeah, so what that would mean is that z is negative, and now if you multiply this, so if x and z are both positive, the first part would give you that xz is at least 0, and the second part here would give you also, since both are negative, this would also give you that xz is at least 0, and yeah, and that would have implied that x is related to z and hence transitive. But like O just pointed out, the catch with this argument is that we're dealing with an equality here. So when you say xy is at least 0, it could be that it is indeed 0. So that is the case that we did not account for in this analysis. So I'll maybe write it here so that it does not cause confusion. So the catch is that this does not account for product being 0 case. Okay, so I'll just take the same counter example that she mentioned. So let's say xy is 0. That could be because y is 0 and say x is minus 2, and yz is 0, that is because y is 0 and z is 3. Now that does not say that if you look at x times z, that is minus 2 times 3, this is minus 6, and this is not positive. So yeah, so that is the counter example. I hope I did not end up confusing with this analysis. Please let me know if there are any questions about this part that we did. Okay. Okay, good. So this relation is not transitive. What about C? Okay, Pratik says this is reflexive, not symmetric. Okay, good. Um, yes, Ojas, you have a question?
Ma'am, I have a question out of this question. I couldn't understand the difference between anti-symmetric and not symmetric.
Oh, okay. Um, okay. So it is possible that a relation is neither symmetric nor antisymmetric. So let me give a simple example of that. Let's say maybe I'll do it graphically. So let's say is okay. So let's say this is a relation which is represented by this graph. Now the question is this symmetric? Okay,
No, ma'am.
good. So Pratik and Ojas, both of you think this is not symmetric because C and D are related, but D and C are not related. So the property of symmetry is violated at this point. And what can you say about antisymmetric? Is this relation antisymmetric? Good. So Pratik says that this is not antisymmetric simply because it's true here that C is related to D and D is not related to C. So this is a good example for antisymmetry. But at the same time, there is a pair of elements here which is AB where the antisymmetry is violated. So such a relation is neither symmetric nor antisymmetric. So the point that I'm trying to make here is that symmetry basically says you must have these double arrows in the graphs everywhere. Antisymmetry says that you should only have one directional arrows in the graphs, if at all you have them. It's possible that there is pair of elements that do not have any arrow amongst them, that is totally fine, but if you have, it should be one directional. So in this case what happens is you have both kinds of arrows, and therefore the relation is neither symmetric nor antisymmetric. So does that answer your question? Okay, good. So uh, let's try to solve this. In asymmetric relations, reflexive pairs are also ruled out. Yes. So that is another point. So whenever you're looking at symmetry and antisymmetry, you're only looking at distinct elements. So you're not talking about symmetry between A and A, or between B and B. So that is taken care of in the reflexive part. So you only look at the distinct pairs. Is that fine? Okay, good. So okay, just give me a minute, please. Okay. Uh, okay. So okay, so let's start with the first question. Is this reflexive? That is one related to one? Okay, this is true because x is 1, so clearly this is reflexive. I mean, no doubt about it. Let's ask symmetry. So x is related. So let's say x is 1, y is 3. So 1 comma 3 is in the relation because x is equal to 1, but 3 comma 1 is not in the relation because x is not equal to 1 here. So this is not symmetric. And that like I think Pratik or Ojas, like one of you asked, this is this does not mean that the relation is antisymmetric. It just says that the relation is not symmetric. Now we have to separately check for antisymmetry. So what do you think? Is this also antisymmetric? Yes. So this is indeed antisymmetric because let's say you have 1 comma y which is in the relation, and then y comma 1 is in the relation. What that would mean is, this means y has to be 1. It can't be that y is some other value. So yeah, so if y is not equal to 1, then that implies that y comma 1 is not in the relation. Is this making sense? So what we're saying is, if uh, x y are related, then it can't be that y x are related unless they are both the same. So what we are essentially saying is x y in R and yx in R, if both of them happens, then it better be that they are the same elements. Otherwise, you can't have this property. So this is indeed an antisymmetric relation. And what about transitivity? So let's say 1 comma, yeah, 1 comma 3 is in the relation because because x is 1, and 1 comma 5 is in the relation because 1 x is 1 again. Then what can you say about 1 comma 5?
Ma'am, I don't think it is a transitive relation
Okay, what is your argument for that?
because
Oh,
1
sorry,
comma
sorry,
5
sorry, sorry.
or
Yeah, go ahead. Yeah.
because when we are talking about 1 comma 3 and 1 comma 5,
Hmm.
then the relation will get would be 3 comma 5. 3 comma 5 does not satisfy our condition.
Yes. Okay. So that does not mean that it is not transitive, but this was not a good example. So let me do it again. So 1 comma y is in R, and y comma z is in R. So what does that say about y? That means y has to be 1. Is this fine? Because Isha, is this fine? Okay, good. So what this means is, what we're essentially saying is 1 comma 1 is in R, 1 comma z is in R. Then what can you say about 1 comma z is the question. So that would clearly be in R. The reason why this happened is, the moment you say x comma y and y comma z are both are in R, it imposes that y is 1. So it also forces this y to take a value, but that doesn't matter for the argument. Essentially, we're comparing this element and this element. So my claim is that this relation is indeed transitive. So are there any questions about okay, so Pratik says the only y that will relate to z is 1. Yes, exactly. So if there are any questions about this part, sorry, then yeah, please do ask. Otherwise, let me know that it is fine. Ojas Kaustub. Okay, okay, good. So I think I'll let you think about the D part. So take this as a homework. If there are any questions about the problems that we did not do in the tutorial, then feel free to ask me in the next tutorial. So try this out, and if you have any doubts, then let me know. So I'll move on to the next question. So this is an interesting question and different from what we saw so far. So let's recall that a symmetric relation is that if A is related to B, then B is necessarily related to A unless they are the same. So you have a set of whose size is 12, and you have defined a relation on on this set. So the question is, how many symmetric relations are possible? So before even we get there, let me ask you, how many reflexive relations are possible?
Ma'am, 2 raised to the power 140,
2 raised to the power
140.
140. Uh, okay. Anybody else? With You are close, but think the answer that I have in mind is slightly different from that. Anybody else? Okay, so I think
Ma'am, it would be 2 raised to the power 144 because we have to multiply 2 to the n.
yes. So it is 144 minus 12. which is 132. Is that what you 2 to the 132? Okay, so let's look at this. So what you do is you draw this in the form of a matrix, let's say. So you have 12 rows here and you have 12 columns here. Now what can you say about the entries in the diagonals?
It would all be one if the set is reflexive.
Exactly, good. So this would all be ones, which means these are fixed. So I can't change this. But what can I say about the entries here? Anywhere else?
We can take as we want 0 or 1.
Exactly. So you can independently have any value to any have 0 or 1 value to any of these entries. So the question now is, how many entries are there which are not on the diagonal? So totally there are 12 into total entries is 12 into 12, which is 144, and the number of diagonal entries is 12, and therefore the number of non diagonal entries is 144 minus 12, which is 120, 132. And now for each of these entry you can independently we can set each entry to 0 or 1. So there are 2 into 2 into 132 many choices, and therefore you have 2 to the 132 many reflexive relations. So is this fine with everyone? Okay, good. So if that is clear, then try this out. So count the number of symmetric relations that are possible on a set of size 12.
Ma'am, I think it would be option C.
Okay, good. So I'll wait for a minute for others to try. Then I'll start with the answers. Okay, so Pratik says so symmetric pairs can be 2 to the 61 plus reflexive pairs can be 2 to the 12. Okay, I think yeah, that is correct. Okay, why are you getting 73 though? You have 12 plus 122. Oh, okay, okay, good. So I think the idea is correct. So let's spell it out. So you have this matrix which is of dimension 12 by 12, and now what are the elements that you have control over is you can have any values here. So you have total freedom over these diagonals, because symmetry does not say anything about the diagonal values. But what it says is, once you write a 1 here, it forces you to write a 1 here. Once you write a 0 here, it forces you to write a 0 here. So whatever you write here, the same should appear along this side. So essentially what you're saying is, you can fix a value for these upper triangular elements, and it would force the values on the lower triangular elements. So the number of entries that you can set is along the diagonals and along this triangle. So that would be 144 divided by 2 plus the 6 entries from here. So you can count it whichever way is convenient for you, but you would end up getting 72 plus 6, which is 70. So you have 78 entries which can be filled, which can be chosen 0 or 1 independently. So that gives you 2 to the 78, which is your option C. So is this fine with everyone? Manisha? Okay, so okay, Ojas has a question. Please go ahead.
Ma'am, why did we add the 6?
Okay, so when I count, yeah, when I count this 144 divided by 2, what, so this is this triangular, okay, I'll just write this. The total number of entries is 144, which is the number of entries in this triangle, which is T, and you have the same number of entries in the triangle, which is T, and then you have the diagonal entries. So when you divide this by 2, you get 72 is the number of entries in the triangle plus d by 2, which is 6 in this case. So you only counted the triangle entries plus the 6 entries here, but you also wanted to count the extra 6 entries, so I just added up that 6 here. Okay, so yeah, I agree, like different people, like each one of us would count that number differently, but yeah, I just calculated it this way, but you would end up getting the same answer, which is 2 to the 78. So um, so I'll just ask, I'll just pose a question for you. I'll not maybe get into the depth of it, but what we asked is, we asked the number of reflexive relations and we have this answer 2 to the 132. Then we asked the number of symmetric relations that are possible, and the answer that we have is 2 to the 78. So natural question that arises is, what is the number of transitive relations that are possible? Any thoughts about it? Okay, so the question we asked is number of transitive relations on n elements. So instead of yeah, instead of 6, sorry, instead of 12, I'm just replacing it with n, and the answer to this is not trivial. So there are research papers that are written on, there are entire papers and papers that are dedicated to only finding this value. So as of now, we know some formula for counting this transitive relations, but we do not know closed form. So this is still an open problem, getting a closed form equation for this value. So this is not something that you'd be, I mean, this is not something that I think anybody would ask you in an exam or your assignments, but it's just a curious thing that I want you to know, so that you can also try it out. It's an open problem, and there are lots of research papers on this. So there are different equations or different formulas for this quantity, and you can take a look at it whenever you have time. I just wanted to mention that. And I think I have, okay, I think I have 3 more questions. Let's see how many of them will be able to take. So I'll cut off at 8, but yeah, let's try to solve all of them. So you have this set 1 2 3 4 5 6, and the question is, which of these subset is a partition of this set?
Ma'am, I think that would be option C.
Okay, good. So that is indeed correct. So this is option C, because when you say a partition, you're essentially dividing it into parts such that they're all disjoint. So a partition says that this is disjoint, and the second point is, if you take a union of them, they should cover all the element in the set. So in this case, let's say you look at 1 2 3, then 2 is common to two sets, so this is not disjoint, so disjointness is violated, and so on. So here again 6 is repeated, so disjointness is violated here. In the option D, 3 is not covered, so your correct option is C, which is it divides the set with 2 4 6 and 1 3 5. So these are the two partitions that you get. So I'll move on to the next question. So yeah, unless there are any questions about this problem. Okay. So the question is that you are given this relation which says that AB are related if and only if the sum is even, and okay, so I'll maybe just quickly recall what an equivalence relation is. So equivalence relation is that a relation which has three properties: it is reflexive, it is symmetric, and it is transitive. If all the three properties are valid, then the relation is said to be an equivalence relation. And
Yes, ma'am. It is equivalence relation.
okay, good. And I'll just define equivalence class, and then you can tell me the number of equivalence class. So what we mean by equivalence class is that this equivalence relation enjoys a very nice property which is not true for any other relation. So if this property is true, then the relation is necessarily an equivalence relation, and if it's an equivalence relation, then the property must hold. So it's a characterization of the equivalence relation which says that it always partitions your set into some finitely many or some it basically induces a partition on the entire set. So this is, let's say, partition p1 p2 and so on. So these partitions are what are called equivalence classes. And what is the property of this? It says that if you look at any two elements within a class, within a partition, they would always be related. So all of these elements would be related, but if you look at elements across the partition, they would never be related. So so in this example, uh, what is the number of equivalence classes that you get?
Ma'am, I think it would be option D.
Option D, which is 3.
Yes. Yes.
Okay. Okay, so
No,
Pratik.
no, no. Option C. Option C.
Okay, good. So Pratik and Ojas, yeah, both of you are right. So the option would be it's option C. So um, yeah, so let's say you have the number 1 in, you put the number 1 in one class, then 2 is not related to it. uh, yeah, Kaustubh, you are also right. So 2 is not related to it because 1 plus 2 is not even, but 3 is related, so you put 3 here. Then 4 is related because 4 plus 2 would be even, and then 5 is related, 5 is here, 6 is here, 7 is here, and so on, because if you add any two odd numbers, you get an even number, and if you add any two even numbers, then you get an even number. So this partition corresponds to the set of all odd numbers, and this corresponds to the set of all even numbers, and you can put 0 here, even numbers. So yeah, I think you all of you got it right. So this is option C. And I see a comment here from Pratik which says that something about refinement of partitions. So what do you mean by refinement of partitions? I am not Sure, could you explain? Okay, we can also take this up at the end of all the questions. That is also fine. But I hope this example was clear. Okay, so I'll move on to the next question. Uh, Sorry. Okay. So um, I'll just read out the question for you and then you can take up some time to solve it. So R1 and R2 are two relations that are defined on the same set A, and what we know about them is that they're both equivalence relations. Now, there are two claims that we're making. The first claim is that their intersection must be an equivalence relation, and the second claim is that their union must be an equivalence relation. So, um, okay, so just to be clear, what we mean by intersection and union is, notice that R1 is simply a set of elements and R2 is also a set of elements. So by intersection we just mean the set intersection, and by union we again mean the set operation of union. So yeah, maybe try this out, take a couple of minutes, and then yeah, we can discuss this.
Ma'am, I think option 2 is correct. Second statement is correct, not option 2.
Okay. um, Okay, so I'll wait for a minute for others to think, and then I'll ask you if you have any idea. I mean, if you would like to expand on that. So I'll just give others some time to think.
Ma'am, option B is correct.
Okay, yes, good. Yeah, do you want to explain? Yeah, Ojas, Isha, Kaustub, any of you. I mean, others are also welcome. So yeah, would you like to?
Ma'am, the recent example was in like a plus b is an even number, and we partition it in odd numbers and even numbers. So let's say they are both two equivalence relations of odd numbers and even numbers, and uh, if we unite them, means if we do union in them, then that would also be an equivalence relation.
The union would be an equivalence relation. Is that sorry,
Yes,
what?
ma'am.
But your answer was that intersection is a equivalence relation, whereas union may not be an equivalence relation.
No, no, ma'am. I said after that statement 2 is correct. I didn't say option B.
Oh, okay, okay, okay. Uh,
Uh, I
oh,
explained it for statement 2 only.
oh, okay. Okay, that is fine. So I'll come back to it. Pratik has raised a hand. Uh, Pratik, I'm not able to hear you. I'm not sure if others can hear though. If somebody is able to hear, then please, yeah, please let me know either. Yeah, yeah, even I'm not able to hear. Um, would it be possible to write in the chat? Okay, so I'll start with the solution. Okay, union won't be equivalence relation because we have exactly that is correct. So yes, I agree with that. So Pratik says that union is not an equivalence relation, but yeah, because the transitivity property may not hold. So I'll come to it. But yes, good, that is correct. So let's look at the intersection part first. So let's ask if yeah. So we want to check if R1 intersection R2 is equivalence relation, or is this an equivalence relation? That is the question. So first property is reflexivity. So um, yeah, so if so we know that R1 is a reflexive is symmetric, there sorry, R1 is necessarily reflexive, and R2 is also reflexive because they are both um, equivalence relations. And if you take an intersection of that, you would only end up getting all the a um, all the pair of A in the R1 intersection R2, because and A is also there in R2 for all A. So if you take an intersection, you would end up getting all these elements in R1 intersection R2 for every A. So therefore this is reflexive. By the same idea, you can also show that it is symmetric, because if AB is in R1 and AB is in R2, then this implies that AB is in R1 intersection R2, but this would also imply that BA is in R2, is in R1 intersection R2. This is because R1 itself is symmetric, so BA is in R1, and R2 is also symmetric, so BA is in R2, and by intersection property you would end up getting that BA is in R1 intersection R2. This is for all AB. So this is also symmetric. Now the question is about transitivity, and the same logic applies essentially. So AB is in R1, BC um, yeah, BC is in R1, and that would imply that AC is in R1. Similarly, let's say AB is in R2 and BC is in R2, that would imply that AC is in R2, and therefore if you take an intersection, you would get AB in R1 intersection R2, BC in R1 intersection R2, and AC in R1 intersection R2. So all the triplets end up getting in the intersection. So this is also transitive. Is this fine with everyone? So the claim is that this is intersection is an equivalence relation. So if there are any questions about this part, then let me know. Okay, good. So let's look at what happens if I change this to union now. Let's do this step by step again. So let's talk about reflexivity. All the pairs A comma A are in R1, all the pairs A comma A are in R2, so they would also end up in the union. So the reflexivity part is valid. If you do that for the symmetry part, so AB is in R1, and that would mean that BA is also in R1, and similarly for R2. Oh sorry, it does not matter whether AB is in R1 or R2 or not, because when you take the union, you would end up taking ABBA at the same time in the union part. So symmetry is also not a problem. The problem that happens is with the transitivity, because it is possible that AB is there in the set R1 but BC is not there, and BC is there in R2 but AB is not there. Therefore, what happens um, is that when you take the union, um, you may not get this AC at all, because it was not there in R1, it was not there in R2. So I'll draw this again. So I'll give you an example. So let's say R1 has that A is related to B, R2 has that B is related to C. So in R1 union R2, you have A is related to B and B is related to C. But does this mean that A is related to C? Yes, exactly. So this is not there. So you can also come up with a small example like this. You can say that um, R1 is that A and B are related, C and D are related. This is R1, and R2 is that AC are related and BD are related. So okay, but when you do R1 union R2, what happens is that you put A here, therefore you're forced to put B because A and B are related, so you put them in the same partition. Then you look at this A and C, so C is also related to um, C is related to A in R2, so you put it here. But now what happens is this pair of BC that got created is not related in R1, it's not related in R2, so you would not get this pair in R1 union R2, and therefore it would violate the transitivity part. So this is a simple counter example for this. So yeah, so what you have is this is not transitive, therefore um, therefore R1 union R2 is not equivalence relation. So the answer is B, which I think, yeah, some of you already got this. So the answer is that the intersection is an equivalence relation, but union may not be. So yeah, I think I'll stop with that. So next we will meet on next Friday from 6 p.m. to 8 p.m. and we will follow the same template. So if you have any questions regarding assignment uh, 2 and 3, then I'll take it up first, and then we will look at the problems on week 5. So that's what we will do, and if there are any questions about this problem that we did, then I'll wait for some time, otherwise feel free to leave. Yeah, thank you for attending. I hope this was helpful.